All right, let's just dive right into this highly requested one-shot explainer on solutions chemistry. If you've ever found yourself totally lost in a sea of concentration formulas or just scratching your head over the rules of solubility, you are exactly where you need to be. Today, we are bringing you that ultimate aha experience, that heavenly realization of physical chemistry concepts where everything just suddenly clicks into place. I'm going to guide you through this, and by the end, you'll see exactly how the invisible world of molecules dictates literally everything around us, from the air we breathe right down to the soda we drink. So, here's our roadmap for today. We're looking at what a solution actually is, the 9 types of solutions, cracking the mole concept, measuring concentration, and finally the rules of solubility.
All right, part 1. What is a solution? Specifically, separating physical mixtures from chemical reactions.
Because to figure out what a solution is, we kind of need to know what it isn't, right? It's super easy to assume that anytime you mix two things together, boom, you've got a solution. But no, in chemistry, the rules are beautifully specific. Imagine we've got 2 beakers. In the first one, we drop a piece of aluminum into some concentrated acid. Instantly, it starts bubbling and reacting. A totally new substance is being formed there. That's a chemical change. But in the second beaker, we stir a spoonful of sugar into water. The sugar doesn't react at all. It just neatly tucks itself between the water molecules, spreading out perfectly evenly. That is a physical, homogeneous mixture. Nothing new was chemically created. And that right there is the strict definition of a true solution.
Okay, so what's actually in that beaker? Let's talk about the solute and the solvent. And do me a favor, completely forget that old middle school rule you might have learned about the lesser amount always being the solute. We are way past that now. The scientific truth is purely about the action taking place. What gets dissolved into what? The solute is simply the substance that gets dissolved, and the solvent is the substance doing the dissolving. It's that simple.
Moving right along to part 2, the 9 types of solutions, states of matter, and rule-bending mixtures.
So, the final physical state of your solution, whether it feels like a solid, a liquid, or a gas, is actually entirely determined by the solvent. And since we've got 3 states of matter for the solute and 3 for the solvent, well, 3 times 3 gives us 9 distinct combinations. Some of these make perfect intuitive sense. Gas and a gas, that's just the air we're breathing. Liquid and liquid, ethanol and water. Solid and solid, that's like making an alloy by melting copper and gold together. But mixing different states, that's where things get really wild.
Let's look at the rule benders. How on earth do you mix a liquid into a gas? Think about highly volatile chloroform. It naturally evaporates so incredibly fast that its liquid particles just seamlessly mix right into nitrogen gas, creating a perfect mixture. Or get this, gas in a liquid. Honestly, when I was younger, I totally thought fish somehow ripped water, H2O, apart to breathe the oxygen. Nope, fish actually inhale trapped oxygen gas that is physically dissolved between the liquid water layers. And finally, gas in a solid. Hydrogen gas can literally just stick or adsorb right onto the solid surface of palladium metal. Mind-blowing, right?
Which brings us to part 3, cracking the mole concept, the foundation of chemical counting. Before we can even think about measuring the strength of our chemical mixtures, we need some math tools. Specifically, how do you count what you literally can't see? Scientists faced a massive problem early on with this. Trying to memorize the tiny, fractional mass of a single carbon atom was basically impossible. You're talking about something with like 23 zeros after the decimal point. They desperately needed a clever, clean shortcut so they could count and weigh atoms on a macroscopic scale.
And the shortcut they found is just brilliant in its simplicity. Think about it like this. Grouping bananas into a dozen gives us a nice, clean number 12 to work with. Well, grouping atoms into a mole does the exact same thing for atomic weight. A mole is just a ridiculously huge group, specifically 6.022 times 10 to the 23rd power atoms. By taking that exact massive pile of carbon atoms, that impossible decimal fraction turns into a perfectly clean, easy-to-remember 12 grams. The mole is literally just a chemical dozen.
All right, on to part 4, measuring concentration, from orange juice straight to analytical chemistry.
Now that we know how to count these atoms, how do we measure the strength or the concentration of our solutions? Picture making some orange juice. You dump a whole flavor packet into a glass of water, and you get this vibrant, punch-you-in-the-face flavorful drink. But if you only use half a packet for that exact same glass, it looks pale, it tastes totally watered down. Concentration terms, like percentages, molarity, or ppm, are honestly just the mathematical way of writing down that exact visual difference on paper. It's just comparing the amount of solute to the total amount of solution.
Now, here is a really fascinating detail about these formulas. We actually split them into 2 separate camps,
temperature-dependent and temperature-independent. Why does that matter? Well, heat gives particles energy, right? It makes them spread out, which expands their volume. Because of that, any concentration formula that uses volume, like molarity, which is moles per liter, will physically change if the room gets hot. Meanwhile, mass-based formulas, like molality, which uses kilograms, mass doesn't care about heat. Those numbers stay rock solid regardless of the temperature.
Let's look at one specific concentration term that always seems to trip people up: parts per million, or ppm. Look, a standard percentage just tells you how much stuff is in 100 parts of solution, right? Well, ppm just tells you how much solute is in a million parts. That's it. Imagine a massive pond. You've got 2 million grams of water, and there's just 20 grams of salt floating around in there. If we scale that down to find the amount for exactly 1 million grams, we just divide by 2. That leaves us with 10 grams. Boom, your concentration is 10 ppm. This is absolutely perfect for measuring tiny, microscopic traces of pollutants in huge bodies of water.
And finally, Part 5, the rules of solubility, saturation, and the temperature cheat code.
Time to face the final boss of our explainer, solubility. This is the ultimate rulebook for whether a solute will actually agree to dissolve into a solvent. And the golden rule here is simply like dissolves like. The molecular interaction is basically the chemistry version of making friends. Particles with similar electrical charges just naturally vibe with each other. Water is polar. It has slight positive and negative charges. Sugar is also polar, so when they meet, those charges attract and they mix perfectly. On the flip side, nonpolar molecules like benzene have zero charges. If you try to mix a nonpolar solute into a polar solvent, they will literally completely ignore each other, like dissolves like.
But hey, even the best of friends have boundaries. Think of a solution like a physical room. An unsaturated solution has plenty of empty chairs. But once that solution hits its absolute maximum capacity, it becomes a saturated solution. It's a crowded room. At this point, any extra solid you try to toss in will just be violently rejected and sink right to the bottom. Unless you use a cheat code. If you apply heat, the particles get energetic, they move apart, and you literally expand the space in the room. This lets you force even more solute inside, creating what we call a supersaturated solution.
But you gotta beware of Le Chatelier's principle here. Nature absolutely hates being forced out of balance. If the process of dissolving naturally releases heat, meaning it's exothermic, and you try to pump more heat into it, the system rebels. It'll actually push the reaction backward, violently throwing solid particles right back out of the solution just to escape that extra heat. So I want to leave you with a provocative thought to ponder. If heating forces an exothermic solution to reject solids, what exactly happens when you heat up an endothermic solution, one that actually loves to absorb heat? Think about how the system would balance that out. I really hope this explainer brought you that sweet, sweet chemistry enlightenment. Keep observing, keep